Welcome to this coding solution walkthrough. Today, we'll be tackling problem number 499, the maze 3. This problem focuses on pathfinding within a maze, where we need to determine the shortest path to reach the destination while considering constraints. Let's dive in and break it down step by step. In the maze 3, the goal is to navigate a ball through a 2D maze to reach a hole. The challenge is finding the shortest path, and if there are multiple shortest paths, selecting the lexicographically smallest one. The maze is represented as a grid where open spaces are denoted by 0 and walls by 1. The ball can move in 4 directions: up, down, left, and right, but it rolls continuously in a chosen direction until it encounters a wall or the maze boundary. Once it stops, it can choose another direction to roll. The task involves determining the path that gets the ball to the hole, or returning impossible if the hole cannot be reached. The input includes the maze grid, the starting position of the ball, and the position of the hole. The output for this problem is either a string representing the lexicographically smallest path to the hole or the word impossible if the ball cannot reach the hole. Let's look at an example. Consider a maze where the ball starts at position 4, 3, and the hole is at position 0, 1. In this case, no matter which direction the ball rolls, all possible paths to the hole are blocked by walls. As a result, the output for this input would be impossible. To understand why the output is impossible, observe the maze layout. The walls create barriers that prevent the ball from finding a path to the hole at 0, 1. Since the ball cannot pass through walls and there are no open paths leading to the hole, the problem conditions dictate that the output must indicate the hole is unreachable. Now, let's look at another example where the ball can successfully reach the hole. In this example, the maze remains the same, but the hole has been moved to position 0, 4. The ball starts at 4, 3, and successfully reaches the hole by following a specific sequence of moves. First, it rolls right to position 4, 4. Then, it rolls up to 0, 4. From there, it rolls left to 0, 1, and finally down to the hole at 0, 4. This sequence of moves rolled represents the lexicographically smallest path to the hole. The solution prioritizes both the shortest distance and the lexicographically smallest order. In another scenario, the hole is located at position 2, 0. Starting from 4, 3, the ball rolls up to 2, 3. Then, it rolls left to the hole at 2, 0. This sequence all is the shortest path and also the lexicographically smallest one. These examples illustrate how the ball navigates the maze by rolling in specific directions until it hits a boundary, and how the shortest and smallest path is determined step by step. There are a few important constraints and edge cases to keep in mind. First, if the ball has no possible path to the hole due to walls or boundaries, the output must be impossible. If the ball's starting position is the same as the hole, the result is simply an empty path. When multiple paths of the same length exist, the lexicographically smallest one is chosen. Additionally, in single-row or single-column mazes, the problem effectively becomes one-dimensional. Finally, ensure that the ball stops only when it hits a boundary or wall, and use a priority queue, such as a min-heap, to implement Dijkstra's algorithm for finding the optimal path. These considerations ensure that all edge cases are handled and the solution is efficient and correct. When solving this problem, one approach we could consider is using a depth-first search, or DFS, without any additional optimization. The intuition here is straightforward. Starting from the initial position of the ball, we recursively explore all possible paths by rolling the ball in one of 4 directions until it hits a wall. At each step, we calculate the total distance traveled and keep track of the path using a string to ensure we can identify the lexicographically smallest path. However, this method has significant drawbacks. The main issue is redundant exploration of states. Since the ball automatically rolls to the farthest point before hitting a wall, certain positions may be revisited multiple times even when better paths to those positions have already been found. This inefficiency leads to excessive recursion and makes the time complexity potentially exponential, as the algorithm wastes time exploring suboptimal paths repeatedly. Instead, an optimized approach, like BFS, can be more effective. Now, focusing on a more efficient solution, we turn to an optimized breadth-first search, or BFS, implemented with a priority queue. BFS is particularly well suited for this type of problem because it explores paths in order of increasing distance, guaranteeing that the shortest path is found. To handle the requirement of lexicographical order, we use a priority queue, or min heap, which sorts the paths first by distance and then by their string representation. This ensures both optimal path length and correct alphabetical ordering. A few key observations allow us to refine our approach further. Since the ball rolls until it hits a wall, the number of positions we need to evaluate is significantly reduced compared to standard grid traversal. By prioritizing shorter distances and smaller lexicographical paths, we avoid revisiting less optimal states. The algorithm proceeds as follows. We maintain a priority queue to store tuples containing the distance, path string, and the current coordinates of the ball. Starting from the initial position, we enqueue all valid moves, rolling the ball in each direction until it hits a wall. For each new position, we calculate the updated distance and path. If the ball reaches the hole, we immediately return the current path. To prevent redundant exploration, we use a visited dictionary to store the shortest distance to each cell, ensuring that we only consider better paths. This approach has a time complexity of O, m*n*log, m*n*, where the log factor arises from maintaining the priority queue. Another approach worth considering is bidirectional search. The idea here is to simultaneously search from both the starting point and the hole, allowing the two search frontiers to meet in the middle. This can potentially reduce the search space compared to unidirectional BFS. However, while the intuition behind bidirectional search is appealing, the implementation is far more complex due to the lexicographical order requirement. Managing the shortest distance and path ordering across two separate search directions introduces additional challenges and makes the algorithm more error-prone. Given these complications, the time complexity remains similar to BFS, but with added overhead. For these reasons, we ultimately chose the optimized BFS with a priority queue as our preferred strategy. It leverages BFS's natural ability to find the shortest path in unweighted graphs while using the priority queue to maintain lexicographical order. This approach strikes the right balance between computational efficiency and simplicity, avoiding the exponential inefficiency of DFS and the complexity of bidirectional search. Each of the approaches we've discussed comes with its own trade-offs. DFS is conceptually simple but inefficient due to redundant state exploration and excessive recursion. The optimized BFS with a priority queue is highly effective for this problem, as it guarantees both the shortest path and lexicographical order. However, it does require additional memory to maintain the priority queue. On the other hand, bidirectional search offers the potential to reduce the search space but introduces complexity in managing two search directions and ensuring path order. Among these, BFS with a priority queue emerges as the most intuitive and scalable solution. It effectively balances performance and simplicity, making it the most practical choice for solving this problem while adhering to all constraints. To solve this problem, we need to guide a ball from a starting position to a destination, which we call the hole, on a 2D grid. The challenge lies in the ball rolling in straight lines until it meets an obstacle, and our goal is to determine the shortest path. If multiple paths have the same shortest distance, we must select the lexicographically smallest path string. To achieve this, we start by defining the core components of our algorithm. First, we use a priority queue, implemented as a min heap, to ensure that we always process the shortest path first. Each entry in the queue is a tuple containing the distance, the path string, and the ball's current position. Additionally, we maintain a visited dictionary to store the shortest distance and smallest path string for each grid cell, which helps us avoid redundant calculations. Next, we define the four possible movement directions: right, left, down, and up, and associate each with a corresponding path string, R, L, D, and U. Finally, we initialize the search by adding the starting position to the priority queue with a distance of 0 and an empty path. The visited dictionary is also updated to reflect this initial state. The algorithm proceeds by implementing a main search loop. As long as the priority queue is not empty, we extract the element with the smallest distance, which guarantees that we are always working on the shortest path available. If the current position matches the destination, we can immediately return the path string since the priority queue ensures it is the optimal solution. For every direction, we simulate the ball rolling by moving it in that direction until it encounters a wall or the grid boundary. We calculate the new position, update the distance traveled, and check whether this position represents a better path than any previously known. If the new distance is shorter, or if the distance is the same but the path string is lexicographically smaller, we update the visited dictionary and push this new state onto the priority queue. It's also important to handle edge cases. For instance, if the hole is unreachable, meaning the priority queue is exhausted without reaching the destination, we return impossible. Additionally, we ensure that the ball stops at the hole if it rolls past it during its movement. This algorithm is a combination of greedy and breadth-first search principles, similar to Dijkstra's algorithm. By using a priority queue, we ensure that paths are processed in increasing order of distance, guaranteeing correctness and optimality. The inclusion of the path string in the priority queue allows us to compare lexicographical order when distances are tied, ensuring that the smallest string is chosen. The rolling mechanics of the ball are simulated by incrementally updating its position in the chosen direction until an obstacle or the hole is encountered, which allows us to accurately model the problem constraints. In terms of data structures, the priority queue is central to implementing this weighted BFS efficiently, while the visited dictionary helps us track the shortest distance and smallest path string for each cell, preventing redundant exploration of suboptimal paths. For complexity, the time complexity is O, m*n*log, m*n*, where m and n are the grid dimensions. This accounts for processing each cell once and using a heap for efficient retrieval. The space complexity is O, m*n*, which accounts for both the priority queue and the visited dictionary. To better understand the algorithm, let's walk through an example. Consider a 5x5 grid with walls, where the ball starts at position 0, 4, and the hole is at 4, 4. Initially, the distance is 0. From the starting point, we explore all possible directions. Rolling left takes the ball to 0, 0, with a distance of 4 and a path string of L. Rolling down takes the ball to 4, 4, with the same distance of 4 but a path string of D. Since 4, 4 is the destination, we prioritize it and return the path string D as the solution. For an edge case, imagine a similar grid where walls block all paths to the hole. If the ball starts at 0, 0, and the hole is at 4, 4, the algorithm would exhaust the priority queue without reaching the destination. In this case, the output is impossible, as the hole is unreachable. This demonstrates how the algorithm handles both typical and edge case scenarios effectively. To solve the problem of finding the shortest path in the maze, we start by importing the heap module, which helps us implement a priority queue for our search algorithm. Next, we define the find shortest way function within the solution class. The function takes three parameters: the maze, the ball's starting position, and the hole's position. First, we calculate the maze dimensions and define the possible movement directions along with their corresponding characters, such as U4 up, D4 down, L4 left, and R4 right. Then, we initialize a min heap to prioritize paths based on their distance and lexicographical order, as well as a dictionary distances to track the shortest path and its associated distance for each position. The heap starts with the ball's position, a distance of 0, and an empty path string. We then process the heap using a while loop. At each step, we extract the position with the smallest distance and its associated path. If the current position matches the hole's position, the function immediately returns the path since we've reached our goal. Otherwise, we explore all possible directions by iterating over the directions list. For each direction, the ball is rolled step by step until it either hits a wall, reaches the boundary, or stops at the hole. During this rolling process, we calculate the new position and the distance traveled. If the hole is encountered during this process, we exit early to avoid unnecessary computation. Once the ball has finished rolling in a particular direction, we calculate the total distance and the new path string by appending the direction character. Now, we check if this new position and path provide a shorter distance or a lexicographically smaller path compared to what we have stored in the distances dictionary. If so, we update the dictionary with the new distance and path, and we push this updated information into the heap for further exploration. This ensures that we systematically explore the maze, always prioritizing shorter distances and resolving ties with lexicographical order. Finally, if the heap is exhausted without reaching the hole, the function returns impossible, signaling that there is no valid path to the destination. This implementation ensures that we efficiently find the shortest path while adhering to the constraints of the problem. Here, we begin by defining the find shortest way function, which takes the maze, the ball's starting position, and the hole's position as inputs. We start by setting up some key variables, rows and calls to represent the dimensions of the maze, and directions, which is a 2D array containing the 4 possible movement directions up, down, left, and right. Correspondingly, we define dir chars to map these directions to their respective characters, U, D, L, and R. Next, we initialize a priority queue, heap, to store our nodes during traversal. The nodes are prioritized first by distance and then lexicographically by their path, ensuring that shorter paths and lexicographically smaller strings are preferred. We add the starting position of the ball to this heap with a distance of 0 and an empty path. A hash map, distances, is used to store the shortest distance and path to each reachable position, with the ball's starting position initialized accordingly. Now, we enter the main loop where we process nodes from the heap. Using a breadth-first search approach, the first step checks if the current node corresponds to the hole's position. If it does, the function immediately returns the path associated with that node. Next, we iterate through each of the 4 possible movement directions. For each direction, we extract the corresponding dx and dy values, as well as the direction character. We then simulate the ball's movement in that direction, starting from the current position. As long as the next position is within bounds, doesn't hit a wall, and the ball hasn't reached the hole, we continue moving, incrementing the step count. If the ball reaches the hole during this simulation, we break out of the loop early. Once we stop, we compute the new distance as the sum of the current distance and the steps taken, and we construct the new path by appending the direction character to the current path. Using the position key, formatted as NX New York, we check if the new position either hasn't been visited yet, or if the new path offers a shorter distance or a lexicographically smaller path than the one currently recorded. If any of these conditions are met, we update the hash map with the new node and add it to the heap for further exploration. After exploring all possible directions and processing all nodes in the heap, if no path leads to the hole, the function returns impossible. Finally, we define the node class to represent each state in the maze. Each node stores the current position, the distance traveled, and the path taken to reach that position. This class is critical for maintaining the information we need to prioritize nodes in the heap and track the optimal path. By organizing our solution this way, we ensure that the algorithm efficiently evaluates all possible paths and returns the shortest lexicographical path to the hole, or determines that it is impossible to reach the hole. To solve this problem, we're given a maze and need to guide the ball to the hole with the shortest path. In this basic example, the maze is represented as a 5x5 grid with walls and open spaces. The ball starts at position 0, 4, and the hole is at position 4, 4. Initially, we define the dimensions of the maze as 5 rows and 5 columns. Next, we decide 4 possible movement directions, up, down, left, and right, represented as tuples with their respective labels. Then, we initialize a min heap to keep track of the shortest paths we explore, starting with the ball's initial position, a distance of 0, and an empty path string. We also set up a dictionary to store the shortest distance and path to each position, beginning with the starting point at 0, 4. With this setup, we're ready to start evaluating the ball's movements from its initial position. The first node we process from the heap is the ball's starting position, 0, 4, with a distance of 0 and no path yet. From here, we evaluate each of the 4 possible directions. Rolling the ball downwards, it moves to the bottom of the column and reaches the hole at 4, 4 in 4 steps. This new path, labeled D, is added to the heap with a total distance of 4. We also update the distances dictionary to record this shorter path to 4, 4. Since the ball has reached the hole, we can terminate the search early and return the path D. This demonstrates how the algorithm efficiently identifies the shortest path when the hole is directly reachable. In this second example, the hole is no longer reachable due to walls blocking the path. The ball starts again at 0, 4, and the hole is at 4, 4. After initializing the heap and distances, we begin processing the ball's starting position. Exploring the downward direction reveals that walls block the ball's path. Rolling left, the ball reaches 0, 0 in 4 steps. This position is added to the heap with the path labeled L, and the distances dictionary is updated. The upward and rightward directions are blocked as well. In subsequent iterations, we process 0, 0, but all possible directions either lead to walls or revisit positions already explored with shorter paths. With no way to reach the hole, the algorithm concludes that the output is impossible. Now, we consider a more complex example where multiple paths can lead to the hole, and we need to select the lexicographically smallest one. The maze is a 5x5 grid where the ball starts at 4, 3, and the hole is at 0, 1. The initialization remains the same, with the heap starting at the ball's position and an empty path. The first position we process is 4, 3. From here, the ball can roll upward to 0, 3, with the path labeled U, or left to 4, 0, with the path labeled L. Both positions are added to the heap, and their distances are updated. The algorithm continues to explore these paths to determine the best route to the hole. As the algorithm evaluates subsequent positions, it identifies 0, 1 as a key intermediate point on the way to the hole. The path UL, which moves upward to 0, 3, and then left to 0, 1, is found to be the shortest. Additionally, since it is lexicographically smaller than other potential paths, it is selected as the optimal solution. The heap ensures that shorter and lexicographically smaller paths are processed first, allowing the algorithm to efficiently determine the result. Thus, the output for this example is UL, representing the shortest and lexicographically smallest path to the hole. One of the most common pitfalls in solving problems like the Maze 3 is ignoring edge cases. For instance, failing to account for empty inputs, single-element arrays, or unique constraints such as cycles and graphs can lead to errors that are hard to debug. Always take the time to think about and verify edge cases when implementing your solution. Another frequent issue is infinite loops in DFS or BFS. This happens when nodes are not marked as visited properly, leading to repeated visits and potentially crashing your program. To avoid this, always maintain a visited set or array to track nodes you've already processed. Additionally, incorrect boundary conditions like off-by-one errors or failing to validate indices in grid-based problems can lead to index out-of-bound errors. These small mistakes can derail your solution, so be meticulous with boundary checks. It's also crucial to be mindful of the efficiency of your solution. A brute force approach might work for small inputs but fail spectacularly for larger ones due to time or space complexity issues. Always analyze complexity and optimize when necessary. Finally, remember that some problems allow multiple correct solutions. If the problem permits multiple optimal paths or configurations, your implementation should account for all of them. Overlooking this can lead to incomplete or incorrect answers. When approaching problems in an interview setting, there are several strategies that can help you perform more effectively. First, focus on pattern recognition. Many problems share underlying structures, such as graph traversal, dynamic programming, or sliding window techniques. Identifying these patterns early can guide you to the most efficient approach. Another key point is balancing optimality with feasibility. Start with a brute force or naive solution to clarify your understanding of the problem, and then refine it to make it more efficient. Interviewers often value seeing this iterative improvement process, as it demonstrates your problem-solving skills. Be sure to articulate your test cases as you work through the problem. Highlight edge cases, average cases, and stress tests to show that you're thorough and thoughtful in validating your solution. Time management is also critical. Spend the first few minutes brainstorming and outlining a clear plan before diving into the code. This ensures you don't waste time backtracking later. A structured approach will make your thought process clearer to the interviewer and increase your chances of success. It's also helpful to study related problems that share similar concepts or techniques. For example, LeetCode problem 79, word search, involves using DFS to navigate through a grid, much like the Maze 3. LeetCode problem 200, number of islands, is another classic DFS or BFS traversal problem that's highly relevant. LeetCode problem 490, the maze, is perhaps the closest in nature, as it also focuses on pathfinding using DFS or BFS. Finally, LeetCode problem 841, keys and rooms, involves graph traversal to check connectivity, which is another useful skill in this context. By practicing these problems, you'll gain deeper insights into grid and graph traversal and become more adept at identifying shared patterns and techniques. There are also alternative approaches that can improve your solution depending on the specific requirements of the problem. For instance, using DFS with memorization is a great way to avoid redundant calculations. By storing intermediate results in a table, you can significantly reduce the time complexity of your solution. DFS is another powerful approach, especially when you need to find the shortest path. Unlike DFS, BFS explores all neighbors at the current depth before moving deeper, making it ideal for scenarios where optimality is key. For problems involving weights or costs, algorithms like Dijkstra's or A** are often the best choice. These weighted algorithms are designed to find the most efficient paths in such contexts. Lastly, dynamic programming can be a game-changer for problems with overlapping subproblems. By transforming the problem into a DP formulation, you can often achieve a solution that is both more efficient and easier to reason about. Each of these approaches has its strengths, and mastering them will make you more versatile in solving complex problems like the Maze 3. Great job! In summary, we explored various approaches to solve the Maze 3, examining their strengths, weaknesses, and complexities. Remember to practice similar problems to reinforce these concepts. Thank you for watching, and don't forget to like, subscribe, and stay connected for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!